And your test 3 will be up to 11.1 only. So test 3 will be, what's that? Chapter 10, 10.1 to 10.4, and then 11.1. Okay. Would you like that to have only 3 sections in your, 5 sections in your test?
That would definitely be easier to study.
Actually, the other way around. Let me tell you the logic. Okay. Let me tell you the logic. Here's the thing though. So think of it this way. From my point of view as an instructor, I'm not supposed to record this. So today I will finish up 11.1 and then go on to 11.2. 11.2 also a long section, so I'm not in any way trying to go fast. But then on Monday, you will see I can actually cover 2 sections in one day. Okay. Oh no, Monday is the test, huh? Hold on. Is Monday the test?
Yeah. So.
Oh, okay. Then, yeah, 11.1b will be in your test 1 and test 3. Okay. Okay. What do I need to cover from the later part? First one, the topic today. First one is a very well-known sequence that mimic exponential function. They use r to the n. Okay, we will discuss that more. And then second, we will talk about monotonic sequence. And then the third one, bounded sequence. And once we get those, combining 3 and 4, and we will have monotonic bounded sequence theorem. And after that, that's basically it. Yeah. So first one, what is it about so special about this? What is so special about this sequence here? That's because we see that quite often, especially at the beginning of our next section. For example, if we have A sub n, the sequence of, let's say, 3 to the power of n plus 2. Which, if you think about it, this is 3 to the n times 9, right? 9 times 3 to the n. And this converges to, does it converge?
It looks like it explodes to infinity.
Yeah, it explodes to infinity. Okay, so I may use the convergent notation, but technically we call that diverge to infinity. Okay, now on the other hand, if I change that 3 into, let's say, 2 over 3 to the power of 2n minus 3, like that. Now this is 2 over 3 to the power of negative 3 times 4 over 9 to the n. Will this be convergent or divergent? That will be convergent to 0. Okay. How do you get that, Thomas? Because of something we learned long time ago with exponential function. Now, when we have exponential function, you will have a coefficient times some base to the x, right? Okay. and that exponential function, let's call it this way, fx equals to c times b to the x. And we learned that the far end behavior, this will be infinity when the base is greater than 1, right? Okay, and it will be 0 when the base is between 0 to 1 when it comes to exponential function. Is it okay? Now, I want to extend this. In our examples that we have here. Notice that the base are +3 and +4/9. Okay. If the base is greater than 1, it goes to infinity. If the base is between 0 to 1, it goes to 0. Now, the thing is, because this is a sequence instead of continuous function, then we may consider what if the b is negative. What can we say? Actually, before I do that, what if the b equals to 0? Nothing to discuss, because if b equals to 0, we have fx equals to 0. Is it right?
Wouldn't, oh no, if b is 0, yeah.
Yeah, if b is 0, then the whole function is 0, then the sequence is actually dead on arrival. The sequence already 0 since the first term. Right? Okay, now, but what happens if the b is negative? We will see two cases. But let's say this b is negative of something positive, okay? Such that our exponential function, or maybe I look at that from, we look at that from sequence point of view right away. And we will have a sub n equals to some constant multiple times negative of positive number to the n, which we can then rewrite as c times -1 to the n times positive number to the n. Now notice that it will create alternating sequence, right? It will create alternating sequence. It will alternate. But at the same time, notice that this guy here will basically follow the situation there, right? So to be more detailed, if the b is even less than -1, then a sub n of c times b to the n will be divergent. Okay, it will be divergent, but not to infinity, not to -infinity. It's basically does not exist. Imagine, for example, if I have, let's say a sub n is -3 to the n. Then it will converge to infinity when n is a very big even number, right? But it will be -infinity if n is a big odd number. You see what I mean? Even if it goes to infinity, we don't call that convergent, we call that divergent, but at least it's still divergent to infinity. We can say it explodes to infinity, right? Okay, but when the b is negative, like in this case, we cannot say it is convergent to positive or negative infinity. Now, you can imagine this is what we call that the shit hits the fan. It goes everywhere. It goes to positive and negative infinity. Okay, so it's divergent to the worst case. It's just like, no, it's everywhere. Okay, Now, on the other hand, if the b is between -1 and 0, if b is -1 to 0, then we will have, actually, it will be convergent to 0. Now, you may wonder why. Think of it this way. This will be c times -1 to the n times something positive to the n, right? But when we take a look on the absolute value, that's basically c times positive to the n. And notice that the positives here will be from 0 to 1, right? And this goes to 0. From one of our theorem, if a sub n converges to 0, then the sequence goes to 0. The absolute of the sequence goes to 0, then the sequence itself goes to 0. Oh, is it okay? Let me see. Do I cover all the case already? This is for the base. This is for the base B. I have 0, I have 1, I have -1. Okay, so if the base here, will that be convergent or divergent?
Divergent?
Divergent to what?
Infinity?
It will be divergent to infinity. Okay, what if it is here?
Convergent to 0.
Convergent to 0. What if it is here?
Also convergent to 0.
Also convergent to 0. What if it is here?
Divergent to negative infinity.
Actually, no, does not exist.
Oh.
Yeah, because you see what happened in this case?
Oh, right.
Right? Okay, now, what happened if it is exactly at 0?
Zero.
Imagine if your sequence is, the base is 0. 0 to any power is 0. So it's already dead on arrival. Right? Okay. Now, how about if the base is 1? 1 to any power is 1. Right? Okay. Now, what if the base is -1?
Alternating?
Alternating what?
I have no idea.
Alternating plus 1, -1.
Oh, okay.
Right? So if -1 to n power, that will be 1 when n is even. It will be -1 when n is odd. And it runs forever. Right? Okay. So
Like
yes,
harmonic series?
no, harmonic is actually something else. It's I think at this time we just say that it's alternating. Alternating 1, -1, 1, -1. Okay. I'm talking about the sequence b to the n here. Okay. So b to the n when the b is exactly 1, that's 1 to the n, that's 1. If b is -1, then it will be alternating -1 and 1. Okay. Maybe I say it this way. 0 to the n, that's 0. 1 to the n is 1. Okay. Any number here to the n will go to infinity. Any number here, b to the n, will go to 0. Any number here, b to the n, will go to 0. This one here, b to the n, is divergent. Okay, now that's for the case of this exponential-like function. Now let's see the second topic. The second topic. Why do I mention this? Because once you can realize that, you know what, this thing here looks like an exponential thingy, then just take a look on the base right away. I think we did that type of question on number 28. Number 28, we have the n term equals to 3 to the n plus 2 over 5 to the n. This is 9 times 3/5 to the n, right? And then we'll say this will be convergent to 0 as n goes to infinity, because the base, or our textbook use r, because the r is 3/5, which is between -1 to 1. Number 32, we can argue quite fast. I think I did number 32 also last time. This time I argue with a better theory behind us. E to the 2n over n plus 2. And we say, oh, you know what? The exponent actually, the limit for the exponent is actually 2. Okay, as n goes to infinity. Oh, that one is not exponential form. Sorry. Number 46. I think I did number 46 also. Number 46, a sub n equals to 2 to the negative n of cosine n pi. And we see, oh, absolute of a sub n is equal to absolute of 2 to the power negative n cosine n pi. But this is alternating. I believe this is alternating. You can try. So this is basically 2 to the negative n. That's 1/2 to the n. Right? So we know this is convergent to 0 as n goes to infinity, because the r is 1/2, which is between -1 to 1, according to our theory. Okay, now, but because absolute of a sub n goes to 0, it implies a sub n goes to 0 as n goes to infinity. Yeah. Okay, now, who's that? Nora asked me question number 55 earlier. Let me do number 56 instead. Let me do number 56 instead. Number 56, we have a sub n equals to -3 to the n over n factorial. Let me separate the top first so that we can see that it is actually alternating sequence. Okay, to go away from the alternating sequence, I put the absolute value. So I basically deal with 3 to the n over n factorial. Okay. Now don't forget that this is in terms of in the absolute value. Now if I go on a bit further, I can rewrite it this way. This is 3 over 1 times 3 over 2 times 3 over 3 times 3 over 4 times 3 over 5 all the way to 3 over n. Is it right? Now notice that uh, 3 over 5 is less than 3 over 4. Agree? And also 3 over 6, 3 over 7, 3 over n will be still less than 3 over 4. Are you okay?
It'd be 3 over each of those numbers factorial, right? Or
Yeah, oh no. No.
well, it would be the same pattern, right? But
I'm not applying the terms. I'm not multiplying the terms. This is the nth term, the absolute value of the n terms. The absolute value of the n term will be the whole thing here. This is absolute of a sub n.
okay.
Okay? Okay. Now then,
Oh no, I see it now.
yeah.
Excuse
Now
me.
then, because the yellow one and the blue one, each of them less than 3/4, then I can say this is less than equals to 3 over 1 times 3 over 2 times 3 over 3 times 3 over 4 times 3 over 4 times 3 over 4 times 3 over 4 all the way to the last term.
Okay.
Okay. Now, how many factors do we have here in total? How many factors we have here?
N.
N factors. That's right. Okay. So if I get the first three away, how many factors do I have here?
N minus 3.
N minus 3. And this guy here will be 9 over 2, right? Okay. So basically we are saying that the term that we have up there is 9 over 2 times 3 over 4 to the power of n minus 3. Agree?
Okay.
Or another way to say it more explicitly, then absolute of a sub n is less than that. But what happened to this guy? It converges to what?
It converges to 0.
It converges to 0. Why? Because
It's between
the R is, the ratio is
or it's, less than 1.
between -1 to 1.
Yes.
Okay, between -1 to 1. Once the ratio is between -1 to 1, then that quote-unquote exponential sequence, you will see, actually we call this geometric sequence. Yeah, we actually call this geometric sequence later on. No, not later on, even in pre-calculus, we learned that as a geometric sequence. Okay, now, then it goes to 0, but because a sub n converges, absolute of a sub n converges to 0, then the sequence itself will converge to 0 as n goes to infinity. Okay. By the way, the notation I use here is a shorthand of limit n goes to infinity of a sub n equals to 0. That's just the same notation. Okay, but once you write limit, then you have to keep on writing limit. I didn't write limit. Do you notice that? I didn't write limit at the beginning. I just simplified each term first and then concluded from there. Now, furthermore, the second part, what is monotonic sequence? A sequence A sub n is increasing if the next term is greater equals to the current term. In some sense, it follows what we learned before on increasing function. When we have increasing function, okay, the slope is positive, right? When you go, the further you go to the right, the higher the value. Now, increasing sequence have the same idea, that the further you go to the right, then the value will be at least equal to, okay, maybe even more. That's for increasing sequence. Now, a sequence is, a sequence is decreasing if the next term is greater equals to, I'm sorry, less than equal to a sub n. Basically, the picture pretty much like this. You see, now this sequence R, this function is decreasing. So the sequence, which is a subset of that continuous function, is also decreasing. Okay, now some terminology. I think they are quite easy to understand. A sequence is strictly increasing if you don't have equal sign here. Now this is strictly increasing. Okay. If we just say increasing means it is possible that the next term still equal. Okay, but when we say strictly increasing, then the next term has to be greater. That's the difference between the word strictly increasing, which is the next term has to be greater, and simply increasing, which means the next term has to be at least equal to the current term. Likewise, for the phrase strictly decreasing, the phrase strictly decreasing means the next term has to be less than. This is strictly decreasing. Okay, and this one is decreasing. Why do I mention that? Why do I mention that? Now, the following sequence, just for example, don't need to write this down. The following example: 1, 1, 2, 2, 2, 3, 3, 3, 3, and on. Is this sequence increasing? Is this sequence increasing?
Yes.
Yes, it is increasing. Is it strictly increasing?
No.
So you got what I mean, right? But not strictly increasing. You see what I mean? Okay. Now, Therefore, we can say this thing though. You must be surprised when I say that is the following sequence decreasing? Is this sequence decreasing?
No.
Hmm? Does it satisfy this rule?
Yes, but not strictly.
So you see that is it decreasing?
You could say it's decreasing, yeah.
Yes, it is decreasing, but it is not strictly. Okay, so constant sequence is actually also decreasing. At the same time, it is increasing. Constant term is increasing and decreasing at the same time. However, constant term is not strictly increasing, nor it is strictly decreasing. Okay, now this difference of terminologies, I think our textbook doesn't mention it. Yeah, the definition that our textbook use, if you have your textbook, please open page 720. Please open page 720. The definition of increasing and decreasing is provided in a way that this, when they write it there, the definition they use is supposed to be for strictly increasing and strictly decreasing, because our textbook use this term, this definition here. They call it increasing if it's greater than, no equal sign. They call that decreasing if less than, without equal sign. Okay, but what they meant is actually strictly increasing and strictly decreasing. Is it okay? Now, I weaken the requirement by using equal sign, because that's the correct one. That's the correct terminology. Now, this difference of terminology actually doesn't make a difference in future. For this class, in future it will make a difference. But right now we are fine. So you can call increasing with or without equal sign. You can call decreasing with or without equal sign. But I would like you to know that there's such thing called strictly increasing and decreasing, which may be constant. Okay, just like this. Okay, when fx, maybe I don't want to mention it. Don't worry about it. Also, we say that a function is increasing or decreasing if this inequality holds consistently for any n, at least from 1, because we start from 1, usually, right? Okay, from the first term and on, it's keep on increasing or keep on decreasing. Now, then we call that sequence increasing or decreasing. Now, definition, the word monotonic, a sequence A sub n is monotonic. It's monotone, okay, if the sequence is increasing or decreasing. If the sequence is increasing or decreasing. You see what I mean? So the word monotonic covers either if it is increasing or decreasing. There's one more terminology. There's one more terminology. The word eventually. Sequence A sub n is eventually increasing or eventually decreasing if a sub n plus 1 greater equals to a sub n. For increasing, maybe I change the color. For increasing one, I use blue color, a sub n plus 1 greater equals to a sub n. Or if it is decreasing, a sub n plus 1 less than equals to a sub n. For n greater equals to some other number which is not 1. The key word that I want to emphasize is the word eventually. That's the key word. Now, take a look on the following example. Suppose, for example, I have a sub n n squared minus 8n plus 4. Now notice that if you use your instinct, this actually is a subset of x squared minus 8x plus 4, whose graph will be something looks like this. Hold on. That will be plus 16. Maybe I make it plus 14 here. So the graph of this function approximately something like this. Okay. You notice that it reached the minimum when x equals to 4. Right? When x equals to 4, it will reach the minimum. Okay. Now, this is an example of an eventually increasing function. Why? Because you can find an n, let's say n equals to 5 or 7 or 9, up to you. Okay, I can find an x equals to a certain number. Let's say I use 6 here. Let's say I use 6. Okay, this is when n equals capital N equals to 6. And every term after that is increasing. You see that? Every term after that is increasing. All you need is you can find a capital N such that every term after that is increasing. So I may say, oh, when capital N is 6, and somebody else say, you know what, my capital N is 10. Fine. Because we don't care about what happened to the first couple terms. When we talk about convergency, we care about what happened when n is really, really big. Are you with me? Okay. So what we will do later on when we talk about monotonic sequence, even though our textbook seems to insist on increasing or decreasing from n, from the very beginning, n equals to, from n equals to 1, but it's actually not necessary. Okay, we just need eventually increasing. Okay, therefore, if you have an eventually increasing or eventually decreasing case, then can you guess what does it mean to say a sequence is eventually monotonic? If a sequence is eventually monotonic, it means if a sub n plus 1 is greater equals to a sub n, or a sub n plus 1 less than equals to a sub n for every n greater equals to a preset number. Okay, now that's what it means to be monotonic and eventually monotonic. The following sequence is monotonic. Natural log of n. This sequence is monotonic, right? In fact, if you think about this, the continuous function, the continuous superposition function for that is ln n, ln x, right? Which we know is increasing. It's increasing, actually it's increasing in the domain. Does it make sense? Okay, so this sequence is not only increasing, and that's all we need. It's actually strictly increasing, right? It's strictly increasing. But we don't need that strong strictly increasing. All we need later on, if we say this, if we say that this is convergent, well, all we need later on is like it's eventually increasing. That's all I need. Okay, because we don't care with the first couple of terms. Anyway, in this case here, this sequence converges to what? Converges to infinity. Okay, so it's actually divergent. Okay, it's actually divergent. How about this guy here? A n, and then the term is n over n plus 1. There are some ways to show that it is monotonic. One thing you can do, the very common one, is you take the continuous superposition function and then do the first derivative. This will be 1 over x plus 1 squared, and this is greater than 0. Right? Okay. So, because the first derivative is positive, then the function is increasing. Therefore, the sequence is also increasing. Is it okay? Now, another way to do that, that's the first way to show that a sequence is monotonic or increasing or decreasing. The second way is you compare the terms. Okay, you want to say, oh, it is increasing, but this time you want to show if a sub n plus 1 is greater equals to a sub n. That's what you need to show. Okay, n plus 1 over n plus 1 plus 1. Is it greater equals to n over n plus 1? But if that were true, then n plus 1 squared should be greater equals to n times n plus 2. Okay, n squared plus 2n plus 1 is greater equals to n squared plus 2n. But if that's true, then 1 is greater equals to 0. But the thing is, 1 indeed is greater than 0. Okay, therefore, the original statement, so a sub n plus 1 indeed is greater than the previous term. So the sequence is increasing. Okay, so those are two different techniques to show that a sequence is increasing or is monotonic. You look at the continuous superposition function, or you compare the next term with the current term. Okay. Now, furthermore, how about boundedness? Bounded sequence. A sequence A sub n is bounded above if A sub n is less than equals to m for every n starting from 1. And of course, we can change that term to bounded below if A sub n is greater equals to m for n greater equals to 1. Okay. So for example, that case there, for example, notice that the n term sine n, is this bounded above?
Yes.
One.
Yeah, it's bounded above by
1.
1. Okay, actually you can say 2 too, right?
Yeah.
Right? As long as you can bound it above, okay? As long as this inequality is true, okay, you can find some number that consistently above that value or equals to that value. So upper bound, we call this one upper bound, is not unique. Okay, you can say bounded above by 1, and somebody else say, you know what, I don't like 1, I like 4. Okay, and somebody say, you know what, I like a unlucky number, 13. Fine, do it. Okay, I'm bounded above by 1 for all n from 1, right? And actually we can also say bounded below by -1 in this case. But again, you can say -2, -4, -10, up to you. Okay. In case that a sequence is said to be bounded, sequence A sub n is bounded. When we say it is bounded, then this sequence has the upper bound and also lower bound for any n. So sine n is a bounded sequence because you have upper bound and also you have lower bound. Okay. Now, how about ln n? Does the sequence ln n has upper bound or lower bound?
A lower bound.
What is the lower bound?
0.
That's right. Bounded below by 0. Well, actually, if you look at ln x, the range is all real number. But in this case, our n only start from 1, right? Is it okay? Now, how about the one that I had earlier, a sub n over n plus 1 is bounded. I think this is bounded below by. It's always positive, right? So it's bounded below by 0. If you want to be even closer to the minimum, it's actually bounded below by 1/2. Whatever the n, the value must be greater or equal to 1/2. You see what I mean? You can try 1/2, 2/3, 3/4, 4/5, right? Okay, all of these numbers are actually greater or equals to 1/2. Okay, but for you to find that 1/2 in some cases is so hard. So don't think too hard. Okay, you just need to find bounded below. What is the lower bound? Find a lower bound, not the lower bound. Not the lower bound. Okay, so I can say, you know what? I don't want to think too hard, Thomas. I know it must be positive. So just say it's bounded below by 0. Okay, is it bounded above? Now, if you imagine the function, this is x over x plus 1, right? Which is equals to 1 minus 1 over x plus 1. Then the rational functions, I wonder if you remember, the rational function says that the graph actually looks like this. That's what it looks like. Oh, something. Oh yeah, that's right. The graph should be x equals to 0 and 0. So it should be this. Okay, so the function itself is not bounded above or below, but the sequence will be bounded below because we start from n equals to 1, right? And it goes to positive infinity. Now you see that it's also bounded above, right? You see the upper bound is actually 1, but if you call that 2, you're totally fine. Okay, so this a sub n here, which is n over n plus 1, is the one has the right to be said is bounded. When we say a sequence is bounded, it means it is bounded above and below. Or n greater equals to 1. Only terminology. Bounded above means you have an upper bound. Bounded below means you have a lower bound. Lower bounded means you have upper and lower bound. Okay. We do not need to find the smallest upper bound. No need. As long as you can bound it above, you're fine. Now, that's about the boundedness. Again, I will insert what you don't see in our textbook, but the book is unfairly used that idea in the problems a lot. That's why I let them introduce that to you. Sequence A sub n is eventually bounded above if the nth term is bounded above by some number for any terms after sun capital N. So the word eventually here means this rule does not apply for the first couple terms, but after the nth term, it is satisfied. Okay, same thing with the word eventually bounded below. If the n term the nth term is greater or equal to some number for the nth term after that capital N. Now you will see that we just need in the next theorem, monotonic bounded sequence theorem. Our textbook called it monotonic bounded theorem. It says the following. Monotonic bounded theorem. Monotonic bounded theorem. Let me state the theorem from our textbook first. Our textbooks say every bounded monotonic sequence is convergent. Okay, I will not prove this. They give us the proof there in our textbook. It takes half page approximately, but that's very technical. I prefer to go with your instinct. Now suppose I have a sequence that is bounded above by this value. Let's call this my capital M, and bounded below by this value. Notice that they use the word bounded. Okay, so it has to be both above and below. And next, let's say the sequence is monotonic. Now you tell me, do you want it to be monotonic increasing or decreasing?
Increasing.
Increasing, okay. Then we will say that the terms, actually the sequence is increasing. Now notice that this guy cannot increase to infinity, right? It's increasing, but it's bounded at the same time. So eventually it has to stop somewhere. Agree? Now, I'm not saying that it will converge to M. No. It doesn't have to converge to M. No. Okay, because this M is an upper bound, that's not the upper bound. So it is possible that it actually converges to somewhere slightly below it. You see what I mean? Okay, so it doesn't, M is just the upper bound, the capital M is just upper bound. It doesn't mean it will converge to M. No, it may converge to something less than M. Okay, but from this picture we know that once it is bounded and monotonic, it must be convergent. Do you agree? Nobody say anything. Okay, I assume you agree. Now, this monotonic bounded theorem is very, very strict. It's very, very strict. I will loosen this theorem a little bit. Okay, I will loosen this a little bit. Which, if you think about it, we can actually see this in two possible cases. It will be convergent if it is monotonic increasing, it's increasing and bounded above, right? Like the case that you saw. Okay, if it is increasing and bounded above, then the sequence is convergent. Do you see that? So notice that in the illustration I gave you earlier, right? I say it's bounded with capital M, lowercase m. and it is monotonic, I ask you, oh, do you want it to be increasing or decreasing? You say it's increasing. Once you tell me that it is increasing, then it will be convergent, right? But notice that I didn't use the lower bound in my argument. Do you see that? I don't use the lower bound in my argument. Okay, all you need is actually bounded above and increasing. Then it must be convergent. Likewise, using the same idea, you can say that as long as it is monotonic decreasing and bounded below, right? Then it must be convergent. Can you follow me? So we actually don't need that to be bounded above and below. Okay, what we need is a bounded above as long as it's bounded above as long as it is increasing. Bounded below as long as it is decreasing, either one of them. Okay, in our original theorem, when they tell us monotonic, we don't know if it is increasing or decreasing. Right? We don't know if it is increasing or decreasing. That's why they need to make it bounded above and below to actually squeeze this sequence cannot go out anywhere. So regardless you are increasing or decreasing, as long as you are monotonic, then you must be convergent. Okay, but if I happen to know that it is actually a monotonic increasing, then all I need is actually the upper bound. Or if I know it's monotonic decreasing, all I need is actually lower bound. Okay, let me loosen the requirement even further. What we actually need is not monotonic. What we actually need is actually not bounded monotonic bounded theorem. What we actually need is eventually. What we need is actually eventually monotonic bounded. Okay, so as long as it is eventually increasing and eventually bounded above, then it is convergent. If it is eventually decreasing and eventually bounded below, that's convergent. Okay, let's take a look on, for example, number 74. Number 74. The question is the sequence increasing or decreasing? A sub n 2n minus 3 over 3n plus 4. Is it increasing or decreasing? Let's do this. I don't want to think too hard though. Should I use the derivative or should I use the... Let me use the derivative. So I say let fx equals to 2x minus 3 over 3x plus 4. Note that fn equals to a sub n. Basically, I need to say that the sequence that we are dealing with originally is a subset of this original function, of this continuous function. Now then I do the first derivative. That will be 3x plus 4 squared, and then in the top we will get 2 times 3x plus 4 minus 3 times 2x plus 3. The bottom one is always positive for any n, for any x actually, except when x equals to negative 4/3. But the top one I will get 6 plus 9, that's 15. Now this is strictly positive for x greater equals to 1. Is that right? So the function fx is increasing. And it is not eventually increasing because even when x greater equals to 1, it's already increasing. So the sequence is increasing. Not in the sense of eventually increasing, because it starts from 1. Now, let's see, is it bounded? Use your instinct a little bit. Use your instinct a little bit. If you see this function here, when you see this function here, what's the horizontal asymptote? Actually, if you think about it, it is convergent to what? Limit of x goes to infinity of 2x minus 3 over 3x plus 4. Okay, if you do it on a scratch paper, what is this equal to? 2/3? Okay, let's call that bounded above then. So a sub n is bounded above by, you can use 2/3, but I don't want to have hard time. I call that bounded above by 1. Okay, claim. The proof. 2n minus 3 over 3n plus 4. Is it always less than equals to 1? 2n minus 3 is less than equals to 3n plus 4. Notice that my n is greater equals to 1, right? So 3n plus 4 always positive. So if I multiply by something positive, then I don't need to change the sign. Now notice that this is always true. Okay, so a sub n is bounded above by 1. Now, then from part 1, we have the sequence is increasing. From part 2, the sequence is bounded above. So by monotonic bounded theorem, a sub n is convergent. Okay. In fact, if you think about it further, it is supposed to be convergent to 2/3. Okay, but they don't ask if it is convergent or not. They just ask, is it monotonic? Is it bounded? But since we know that it is monotonic increasing and it's bounded above, then it must be convergent. Okay, but we have not answered the question converges to what. No. I would like to do a couple more problems from this section. I don't think this type of question will show up in my test 3, but in fact, I don't think it show up in any one of my tests, unless I give it to you as a bonus question. Question number 79. So the sequence is square root of 2, 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 square root of 2. And you go infinitely far. The question is find the limit. Okay. I will show you to find the limit, but the technique is totally off. So the technique I use here is totally off, but I want to emphasize that even though the technique is totally off, it teaches us something very important. What is that very important? Suppose A sub n is convergent to the limit L. Can you tell me what is the term A sub n plus 1 convergent to? It will converge to L also. Can you follow me? If the sequence converges to L, then the sequence of the next term will converge to the same number, L. Think of it in this example. I hope this is simple enough. N over n plus 1. We know that this converges to 1. Right? Okay. But think about what happens if I change the n to n plus 1. This is n plus 1 over n plus 2. This will converge to what? Also converge to 1. You see that? Okay. So I will use that idea here. A sub n is square root of 2, square root of 2, square root of 2. Basically, I have n 2's there. Okay. Now, suppose A sub n, converges to L. We need to find that L, right? They tell us find the limit, so it must converge to somewhere. Let's call that L. But because A sub n converges to L, then what happened to A sub n plus 1? According to what I show you there, it will also converges to L. Okay? Now, the thing is, if you think about that, notice that A sub 2, the second term is the square root of 2 square root of 2, which I can write as square root of 2 times A sub 1. Okay. In fact, A square root of 10, the 10th term is square root of 2 times the 9th term. Right? So in general, you can see the next term is equal to square root of 2 times the current term. Can you follow me so far? This type of question actually show up a lot in a lot of math competition problem. Okay. Now, but then if A sub n converges to L, therefore A sub n plus 1 also converges to L, then we will have this equation, right? Then you can solve for that L already. So L squared equals to 2L. Okay? Either L equals to 0 or L equals to 2. Right? But we know that L cannot be 0. Yeah. L cannot be 0. So it must be L equals to 2. Why L cannot be 0? Well, because every term is positive, strictly positive. That's one, it's strictly positive. In fact, we also see that from the equation here, we also see that the next term is increasing. Okay, the sequence is increasing. Right? If it is already positive and it is increasing, it cannot converge to something less than positive. Okay, that's why then this will be true. Notice that I can change this question and make it, I vary that into, for example, I can vary this question into, for example, this thing. A sub n plus 1 equals to square root of 3 A sub n. You see what I mean? And that's still convergent. In fact, it will converge to 3. Another one, the next term equals to the square root of 2 plus the previous term. And the first term is square root of 2. So square root of 2, square root of 2 plus square root of 2, square root of 2 plus square root of 2 plus square root of 2, and on. For this one here, square root of 3, square root of 3 times square root of 3, square root of 3 times square root of 3 times square root of 3. Okay? I think that's all. Actually, what I mentioned here is number 80. Number 80. Okay, we can find the sequence right away. I mean, we can find the limit right away. Even though in number 80, they asked us to find to show that it is increasing. Second, it is bounded above. Okay. That's for this 11.1, and this is where your test will end. Let me give you the suggested homework first, and then I give you a break. Suggested homework, I think last time we already done up to, I asked you to do up to number 53. So I would like you to start from 55. Number 59. You don't graph it though. 59, 61, 63, 65. I'm sorry, not 65. 63, and then number 73, 75, 77. Okay, that's for this. We take a 10 minutes break. We come back at 6:05. Uh-oh. How long did I not record it?
I think since the break.
Oh, no way. Wow.
I usually pay attention to that.
Yeah. Oh, sorry. So, yeah, I hope my note is clear enough. Oh, wow. So this is the definition of sequence, and from a sequence we build a series, which is always mean infinite series. Okay, but to compute the sum of a series, okay, this basically the series, we approach that by first finding the partial sum. Now, nth partial sum, denoted by S sub n, is the sum of the first n terms. Okay, it's the sum of the first n terms. And the sigma notation, the summation notation is using this sigma notation, where the sigma notation is capital M that you rotate 90 degrees counterclockwise. Okay? And that's a capital block M. Now, this is not a summation notation. No, it's not. It looks like one, it's not. Okay, my mom likes to say that I look like human, which means I'm not. Okay? Okay, if you look like one, it means you are not. It's just like, Thomas, your limit is human. If you want to be mathematically sophisticated, right? Your limit is human, but you are not. Well, anyway, now, this is not summation notation, okay? Yeah, Thomas, you're so picky. I'm picky. I'm picky. That's why a lot of students don't like me. But those people who actually survive my class, they do very well in the next class. Okay, why? Start from a good notation though. Now then, we say that the infinite sum, the series, is convergent if this partial sum converges to a finite number. Okay, now, so we get the partial sum and then we push that partial sum to the infinite sum. The idea that we use is the same to the way we did integral to infinity. I think that's chapter 7.11 or 8 point something. I don't remember. It's a long time ago. Okay. Now then, one of important series that we need to deal with is geometric series that has this pattern. Geometric series has this pattern. It has the first term, we denote it by A, sometimes A sub 1, and the ratio R to the power of n minus 1. Okay, now then, the partial sum will be given by this formula. The partial sum will be given by that formula. And if the ratio, if the R is between -1 to 1, then that partial sum will be convergent. That partial sum will be convergent. It converges to this formula. Okay, but keep in mind, we need to look at the ratio though. Okay, I have an example next to it. Basically, if you have some number times the ratio to a function of a linear function of n. Linear function of n on the exponent. Okay, because you can always rewrite it. You can always rewrite it into the first term, right? Okay, into the first term, the ratio, and the exponent to be n minus 1. Okay, now I have the proof here, which you can see in the book, how we prove that. Okay, this is the consequence. This is, you can call this the summary for geometric series. And then if I have number 18 as an example, what will the summation notation look like? Well, it will be from n equals to 1 to infinity. Okay, the first term is 4. The ratio is 3/4 to the power of n minus 1. This is my first term. This is my, oops. This is my ratio. And my exponent always n minus 1. Okay, the sequence is geometric sequence, but because I put a summation notation in front of that, it becomes geometric series. According to our formula, this is the infinite sum. That's for number 18. Now, how about number 24? How about number 24? We have the sum of n equals 1 to infinity. Oh, sorry, actually n equals 0 to infinity. Okay, of 1 over square root of 2 to the n. Okay, now notice that this is not starting from 1. It starts from 0. Okay, but at the same time, notice that it has the pattern of something times a ratio to linear function of n. Okay, so if you ask me the infinite sum, then all I need to know is what is the first term. The first term is start from 0, right? Okay, so the first term is
1.
1. How about the ratio?
Is that 1 over radical 2?
1 over radical 2, that's right. And notice that this 1 over radical 2, 1 over radical 2 is, the absolute is less than 1. Okay, so we have infinite sum, right? The infinite sum will be the first term over 1 minus the ratio. Okay, which is equals to radical 2 over radical 2 minus 1. You know what? I don't like to have radical, especially with subtraction at the bottom. Let me multiply by the conjugate, square root of 2 plus 1 on the top of square root of 2 plus bottom. I get 2 plus radical 2 over 1. That's 2 plus radical 2. But Thomas, hold on. That guy, that series doesn't look like the general pattern you showed us earlier. That's true. But simply because it doesn't look like 1 doesn't mean it's not 1. Okay, just like what I said earlier, simply because you look like 1 doesn't mean you are 1. Okay, simply because Thomas looked like a person doesn't mean he's a person. He may be the beast, whatever, Thomas. Okay, but the best way to really see it, maybe you do the first couple of terms. The first term is 1, right? What is the second term? 1 over radical 2 plus 1 over radical 2 squared plus 1 over radical 2 cubed, right? Okay, and on. Now I can rewrite that using starting from 1. to infinity. What is my first term? 1, right? My ratio, 1 over radical 2 to the n minus 1. Okay, I can do one more problem. Number 26. Number 26, the sum of n equals to 1 to infinity. This is e to the n over 3 to the n minus 1. It's kind of hard to see if this is geometric. I know it will be geometric, but to convince you, and if this were in your test, I need you to convince me by rewriting this sequence here into something look like our general sequence, the general geometric sequence. Okay, that will be e to the n on the top. At the bottom, I have 3 to the n times 3 to the negative 1, right? Which is the sum of from n equals to 1 to infinity. What happened to this guy? What happened to this guy?
Is that 1/3 or no?
Yeah, 1/3 at the bottom. So it goes up,
3.
becomes 3, right? Okay. Now then, what happened to this guy? That's e over 3 to the n, right? But this is not yet though. This is not what I need yet. Why? Because the exponent is supposed to be n minus 1, right? Notice that the exponent here, in our general geometric sequence, it has to be n minus 1. Then modify that further. This is 3 times e over 3 to the power times e over 3 to the power of n minus 1. Okay, which will be the sum of from 1 to infinity of e times e over 3 to the power of n minus 1. The first term is see, it already fits that pattern. The first term times the ratio to the n minus 1, right? Okay, so the first term is e. The ratio is e over 3. Now e is approximately 2.72, approximately, divided by 3. Divided by 3, that's definitely less than 1. See, right? Okay, so the r, the absolute of r is less than 1. Therefore, we can find the infinite sum, which will be the first term over 1 minus the common ratio. Multiply the top and the bottom by 3, I get 3e over 3 minus e. Okay. For this guy here, I would like you to do a little problem, some problems, suggested homework from this 11.2. Let me call it 11.2a, the first part. I won't be able to finish it. That will be number 3. And then number 16, more into conceptual question. Number 17 to number 25. Actually, you can also try number 31. Number 31. Number 37. Number 38. That's actually another interesting one. I think that's all for now. And on Wednesday next week, I will continue from this 11.2. Okay, then that's for today.
Thank you.